So in this lecture, we are going to find the relation between electric field and electric potential. Now, according to the definition of electric potential, it is the amount of work done by the external force in bringing a unit positive charge from infinity to the particular point very slowly. Here, very slowly means without any acceleration. So, based on this definition, we will be finding the relation between electric field and electric potential. Now, suppose this is a point P at which we have to find the electric potential. So, it means that I have to go to infinity and bring a charge of 1 coulomb from infinity to this particular point very slowly. So whatever work I will do in bringing this charge, that work will be equal to the potential of this point. And in this region, in this whole region, there is some electric field, suppose which is given by E. This E may be constant or it may also be variable. So I have gone to infinity and now I am bringing the charge. And suppose I have reached at this particular point. And this is some charge q, although I had to bring a charge of 1 coulomb, but suppose we bring a charge q coulomb. Now on this q coulomb, if it is positive, this electric field will exert an electric force, and this electric force will be equal to q e. Due to this electric force, an acceleration may be produced. Now here, as it is written that very slowly, so it means that acceleration must be 0. So we have to apply an external force in the opposite direction of the electric force. So it means that the external force which we have to apply, it is equal to minus electric force, which means that the external force is minus QE. So the external force which is opposite of electric force, and with this external force we have to go towards this point P. So suppose I go a very small distance dr. So the work done by the external force dw, it will be F external dot dr. So this dW will be minus Q E dot dr. So the total work done will be integration of dW. So total work done is integration of minus Q E dot dr. And initially we were at infinity and finally we are at a point P. But this is the work done in bringing a charge of Q coulomb, not a charge of 1 coulomb. So the potential, which is equal to the work done in bringing a charge of 1 coulomb, that can be written as W upon Q. So this potential will be, if we do W upon Q, it will be equal to potential at the point P minus integration of E vector dot dr vector from infinity to the point P. So this is the relation between electric field and potential. Now, according to this relation, as we can see that electric field is a vector, so this electric field can be written as Ex I cap plus Ey j cap plus Ez k cap. Dr will be written as Dx I cap plus Dy j cap plus Dz k cap. So if I put the values, because both of them are vectors, so Vp will be equal to minus integrating from infinity to the point P Ex dx plus Ey dy plus Ez dz. If I separate all these three, I will get the P point as the potential at the point P as minus integration Ex dx and minus integration Ey dy minus integration Ez dz. And the limits in this case will be from infinity to the x coordinate of the point P, then from infinity to the y coordinate of the point P, then from infinity to the z coordinate of the point P. Now this relation, what we can do is, now this relation shows that potential actually depends on the electric field along x, y as well as z. Suppose Ey and Ez are 0. So in this case, the second term and the third term will be 0. So Vp will be equal to integration of minus Ex dx from infinity to xp. Now if we integrate electric field, then put a minus sign, we get Vp. So if we do just the opposite, we differentiate Vp with respect to x, assuming that there is only electric field along the x axis and there is no Ey and Ez. So this is partial differentiation. Minus dv upon dx, this will give us ex. In the similar manner, suppose ex and ez are 0. So we will get vp is equal to minus integration from infinity to yp ey dy. So when we assume that ex and ez are 0, then in this case we will get ey is equal to minus, this is called partial differentiation of v with respect to y. And the last case will be that suppose ex and ey are 0. So vp will be minus integration ez dz from infinity to zp. So then ep or ez will be minus differentiation, partial differentiation of v with respect to z. We can see here there is a question which says that the electric potential in a region is represented as V is equal to 2x plus 3y minus z. So we have to find the electric field. Now this potential depends on x, y as well as z. If I partially differentiate this with respect to x, so 2, and here as we see there is x, so differentiation of x will be 1. Now, when we partially differentiate with respect to x, we assume that any factor of y or z will be treated as a constant. So, this 3y we can treat as constant. So, differentiation of constant will be 0. And this z also we can treat as constant. So, differentiation of z will be 0. So, dy upon dx will be 2. In the similar manner, if I do dv upon dy, so this 2x I will take as constant, and this 3y, so I will write here 3, and differentiation of y will be 1, and z, so there is, it is also treated as a constant, so it will be. Now del v upon del z, 2x will be treated as a constant, 3y will also be treated as a constant, and for this z, differentiation of z will be 1, so we will have minus 1. Now ex is minus del v upon del x, it will be minus 2. Then ey, it will be minus del v upon del y, so it will be minus 3. Then ez, which is minus del v upon minus z, so this will be 1. So E will be minus 2i cap minus 3j cap plus k cap. This will be, and if I have to find the magnitude of this electric field, I can write under root 4 plus 9 plus 1. So it will be square root of 14.